Let's start here with a learning check. Pause the video if you need to. We did these with the heart. We're going to be talking a lot more about pressure this week. So not just pressure in the left ventricle, which I will put up the answers here. Here's the answer. So in the left ventricle, the pressure goes down to 0 in diastole, in relaxation. And during contraction, 120. And this is average. So it'd be systole. We don't normally talk about blood pressure within the heart when we're talking about human function, right? So at the artery, the brachial artery is where blood pressure is measured clinically. And that's here what's measured, what's labeled. So 120 over what's that? 80 is typical blood pressure. We're going to spend all next week talking about maintaining that pressure at the arteries so that we can have continued flow throughout this systemic circuit. Notice blood pressure does drop dramatically throughout circulation. But in order to continue have flow, we do need to have this pressure maintained. So that's all going to be next week. Pressure is important for flow. So before we go into that, I want to tell you a little bit more about pressure and kind of a little bit of the physics behind it. So we've mentioned some of this before related to millimeters of mercury being the unit by which we measure pressure. Pressure is just force over an area. So in this example, the force is from the air on this water bath, and then this barometer is measuring air pressure. Our body works a little bit differently, but we have baroreceptors that we have talked about briefly as types of sensor receptors that do a similar thing. They're detecting the force over a given area. And then the units for that is millimeters of mercury. The reason it's millimeters of mercury is because historically this was measured in mercury by a barometer. So it's more of historic units. Okay, pressure is important because it is going to allow for flow. So let's look at that. We are interested in gases and liquids at various times in this class. Liquids is going to be this week annexed blood. This principle of physics applies to other fluids as well. In this class, we're going to see blood, and then we're going to see air as a combination of many gases, as well as specific gases, oxygen, carbon dioxide, when we get to the respiratory unit. The same principle applies to all gases and liquids that can move via bulk flow due to pressure differences. Remember, it's a type of gradient. A pressure difference is a pressure gradient. So in this example here, we've got pressure 1, let's say, is higher than pressure 2. It has to be in the scenario because this gray line here is indicating flow, movement of either a gas or liquid. So this gradient allows for that passive flow when you have a pressure difference. The difference between pressure 1 and pressure 2 would be delta P, right? In this case, it would be P1 minus P2. Usually the bigger number would be first. So let's see a couple of examples of this. Just practice this. In this case here, system 1, this tube up here, is there going to be any flow? No, no flow. There might be just some random movement of whatever the gas or liquid in the tube, but no net flow. Whereas down here, which way? Right to left. So high pressure to low pressure. That's the drive to cause fluid movement if this is a fluid system. Again, we're going to be doing blood flow first this week, so it would be the movement of blood. Um, all right. So, of course, it gets a little more complicated than just flow and pressure because in this system, we also have resistance. So, resistance is friction due to the system. This equation here is describing the pressures that influence flow, the, the factors that influence flow. One of them is pressure. Change in pressure, again, so P, for example, P1 minus P2 in this scenario. And then you take that difference and you also divide by resistance. So the higher P1, the higher the flow, the lower P2, the higher the flow, but also low resistance is going to increase flow. High resistance is going to decrease flow. This equation here, if you've had physics, this is the same as Ohm's law. You don't need to know this, but if you have had physics, this can help to connect this. Ohm's law says that the current of a system is equal to the voltage over resistance. Same thing, right? Flow is the current flow or gas flow. Um, Voltage over resistance in that case. So same equation. Okay, so if you um, want to increase flow, how would you do that? What variables could you change? To increase flow, you could increase P1. This might be pressure closer to the arteries, so arterial pressure. You could decrease P2. So the P2 could be pressure further along in circulation in the arteries, or sometimes when we talk about it with this, we talk about the veins, even though there are capillaries in between there. It's 0.1, 0.2 in circulation. So that could be that. Or what's the last way? We could decrease resistance, right? Decreasing resistance would increase flow. For the human body, the resistance we're interested in is the resistance of the entire circuit as it's pumped through. So actually, I will do that on the next slide. So let's apply this to the human body. Um, Blood flow coming out of the aorta is cardiac output, right? This is the volume of blood that is pumped and then circulates, going into circulation. So this is flow, okay? Cardiac output. That pumping of the heart creates pressure, right? So we've got some pressure in this system. In the human body, the pressure, so this is, let's say this is P1 and P2, the pressure at the vena cava is pretty much zero. P2 is zero. So when we talk about pressure, we can just consider P1. Okay. So let's actually start writing out this equation. Same as before, cardiac output flow equals pressure. I can just put P1 because P2 is zero. So I'm just going to write that as pressure, parentheses P1, over resistance. Where's my resistance? It is represented down here. SVR stands for systemic vascular resistance. It also sometimes is abbreviated TPR, which is total peripheral resistance. Same thing. This is the resistance due to all of the blood vessels that blood has to travel through in the body. We'll talk about how this can be changed by changing the size of the blood vessels, but regardless of whether, even if it's just a set number, it's a number, right? There's resistance due to the fluid having to pass through the vessels. We'll talk more about this. So that's what our resistance is. Okay. Um, you could, the same way of to write this would be we can multiply both sides by SVR. So pressure equals cardiac output times SVR. And we'll see this equation again, and it's actually I will put that here. The name will have for pressure have mean pressure here, mean arterial pressure, mean arterial pressure. Abbreviation for that is MAP. We don't have enough acronyms already. So MAP equals cardiac output times SVR. And that's true again because the pressure at P2 is about 0. So we can just use P1 for our pressure number. Okay, another way to diagram this is here. So similar thing here, MAP is a function of the cardiac output that's being pumped in, here represented by a syringe, cardiac output, and then also SVR, represented here by adjustable screws. So again, this can vary in the body. It's a given number at a certain time. We don't actually know that number, but it's the other factor that you can imagine. The higher the cardiac output, the higher the pressure, the higher the resistance, the higher the pressure as well. Lower cardiac output is going to lower the pressure at this point. Lower resistance is going to lower that pressure. So they're both positively contributing. Okay, one last thing about mean arterial pressure right now is this equation is really helpful for talking about the factors that influence blood pressure. For example, we talked about cardiac output. Increasing heart rate is going to increase blood pressure because we know heart rate increases cardiac output. We'll talk more about SVR, the factors that influence that next. But before that, there's another equation. So we can't measure cardiac output and SVR in the human body. So clinically, to measure mean arterial pressure, we're going to measure the brachial artery. I'm not going to go over this in detail right now. You're going to do this in lab. If you haven't already, use a blood pressure cuff to measure brachial artery pressure, which is approximately equal to like the aorta. It's close enough. It's giving us mean arterial, actually, I'm sorry, it's giving us blood pressure, like it says up there, and it will give that to us in systolic over diastolic is here 120 over, I'm sorry, this one's actually 70 in this case, right? It does vary. Okay. So if we want to calculate mean arterial pressure, how do we do that? So first of all, it's not just an average of these two numbers. So we're not just going to take 120 plus 70 and divide by 2. We're not going to do that. Because I know the math for a different number, let me switch to the next slide and do this here. So for the MAP, mean arterial pressure calculation, actually calculating this in a living organism, let's say we have a person who's 120 over 80 is what we calculate with the blood pressure cuff. You might think we're just going to add those together and divide by 2. That would be 100 millimeters of mercury. That is not correct. And I want you to think about, use this image over here to think about why. We don't want to just take the average of those two numbers because the heart doesn't spend equal time at those two pressures. It spends more time in diastole, about 2/3 of the time. It spends only 1/3 of the time in systole. So could you figure out how to use those numbers to calculate, again, this is systole, this is diastole, diastolic blood pressure. We are going to calculate MAP by it is equal to 2/3 times where it's spending 2/3 of its time, the pressure for 2/3 of the time, plus 1/3 multiplied by where it's spending 1/3 of its time. Hopefully this makes sense. You will see other equations places that it actually turns out it's the same math, right? Like it's um, the same equation just rearranged. This one makes the most sense to me because of this graphic that it's spending 2/3 versus 1/3 of its time. So you're just multiplying by time. You're taking into account time as a factor here. If you do this math, you get 93.3 repeating millimeters of mercury. This is less than 100, right? Which makes sense. 100 was halfway between the two numbers, but our heart spends more time in diastole. So the number is going to be lower than the average of the two. So always check your math like that. This number is then used to, in some clinical situations, right? You go to the doctor, usually they give you 120/80. But one number is nice to do certain calculations. Clinically or in terms of research. So this would give you a single number that represents the heart, the average state your heart is in, it providing, not your heart is in, the pressure that your vessels are experiencing at the arteries over time.